Hi, I'm Guo Chaoxie at the Chinese University of Hong Kong, Shenzhen. I'm here pleased to share with you our current research, bucket-based expiration algorithm. Nowadays, temporary data with expiration time is widely used. A common usage is user section storage. When the client signs in, the server will set one section and associate it with an expiration time, like 1 hour, for example. Then the server will respond to the client with the session token. For subsequent requests, the client only needs to attach the session token with its request, and the server will identify the user based on the token. If the token is not expired, its expiration time would be updated and a normal response would be returned. Otherwise, it will return an error. For those applications using a memory key value databases, we cannot remove non-expired data to cause bad user experience, while we also want to save more memory for more users. Therefore, everything expired data efficiency will become an important issue. To have an efficient eviction algorithm, we should retain all non-expired data, evict expired data efficiently to reduce memory usage as much as possible, and meanwhile have an acceptable overhead, not decreasing the throughput too much. Since our main implementation is based on Redis, I would like to briefly introduce how Redis evicts expired data first. Redis uses a hash map called expires to store the expiration information key by key. The value of each key would be the expiration time in Unix time. As we know, the time complexity for a hash map get and stat is O1, and for n keys with expiration, it will need ON space. Using expires, Redis has two evictions. A passive one triggered when a get or set operation requires it to check the expiration time of a key, and an active one that will periodically scan and evict expired keys. For the active evictions, Redis will execute 10 iterations every 100 milliseconds. For each iteration, if time permitted, it would sample 20 keys and evict all expired. If the proportion of expired keys exceeds a threshold, say 25%, it will go to the next iteration. Otherwise, it will break the current iteration. Consequently, Redis active eviction is likely to germinate with no more than 25% expired keys. The main techniques for the randomized sampling is its low efficiency. As the proportion of expired keys approaches 25%, more redundant scans on non-expired keys will occur. That might be even triple of the number of expired keys. As a result, it may fail to evict expired keys in time. Here we propose our bucket-based expiration algorithm. We group keys expired simultaneously into a bucket to avoid those redundant scans on non-expired keys. A key characteristic we used is that most applications will have a finite or fixed TTL, say 1 hour for example. Every operation will delay the expiration by 1 hour, but no expiration will be brought forward. With such property, we could use a limited number of buckets to group and evict keys expired at the same period of time. Let's have a look at the data structure. We inherit the hash map expires from Redis directly to store the expiration for each key. Besides, we create an bucket. Each bucket is a set of keys and is associated with a time record. Moreover, a pointer pointing to the current bucket will be used. Each expiration time will be mapped to a bucket. The bucket ID is calculated by first divide expiration in milliseconds by a base, then module the quotient with the number of buckets n. For example, we have a Unix time in milliseconds here. We first divide it by 1000 and get a time, a kind of discretization to get the Unix time in second. Then we modulate it by 1200. Finally, we have 559 as its bucket ID. In short, we will store expiration in two possible places. Firstly, we will always store it in the hash map expires. Moreover, we may save the key name in its bucket if no bucket condition. Bucket condition means the key's corresponding bucket's time is a match with the key's time. In such case, we cannot add it to any buckets but only leave it in hash map expires. Here are several operations to maintain buckets. For set expire, we first try to remove it from the previous bucket, update its record in expires, and insert it into the new bucket if no condition. For remove expire, we will remove its record from expires and its corresponding buckets. For get expire, we directly access it from expires. Since buckets and expires are implemented in hash maps, the time complexity is O1, and one key could only have at most two records in buckets and expires. So the space complexity is ON for n keys. After introducing our modification to the data structure, let's see how the hybrid algorithm works. We will first try to check all buckets sequentially. By checking the time for a bucket, we know if all keys inside have expired or not. If yes, we will remove all keys inside and reset the time of a bucket. As long as we have time left, we will move the current pointer forward. If we still have time left after scanning all buckets, we will run the original Redis expiration algorithm to evict keys on hashmap expire. Here's an illustration with 3 buckets and base 1000. So we discretize the expiration time into seconds. We assume our computation power allows no more than 2 evictions per active eviction cycle. At time 0, we first set expire for A at timestamp 1023. It is added to bucket 1 and expires, and the time for bucket 1 is now 1. Then we set expire for B, and we set expire for C. In the end of the second 0, 3 keys are inserted into 2 buckets and no condition so far. At time 1, we changed A's expiration into 2023. So A is moved to bucket 2, and the time for bucket 1 is reset. We also set expire for D. When we remove expire for C, we will remove it from both bucket 2 and expires. At time 2, we set expires for E in timestamp 5015. However, since 5 modules 3 is 2, and the bucket 2 contains keys expired in time 2, a bucket collision happens, and E could only be saved in expires but no buckets. At time 3, the current pointer will scan through bucket 0 and 1, and when it reaches 2, it finds bucket 2 has expired. Then, 2 keys B and A are evicted and no time for evicting D. At time 4, now D is able to be evicted. Finally, we will need the original Redis eviction to evict E from expires, since it does not belong to any bucket. We will briefly have a comparative analysis here. Suppose the threshold for Redis expirations is alpha, and the proportion of expired keys over all keys is P. We scan M keys each time, then on average, P M keys are expired, and 1 minus P times M keys are redundantly scanned. For Redis original one, as more spark keys are removed, P decreases and approaches to alpha. The utilization, which is the proportion of spark keys over all scanning keys, decreases, and more redundant scans occur. As a result, we will have lower eviction efficiency. For example, assume we have 100 keys, alpha is 25%, M is 20, and P is 40%. Then, on average, Redis original one could only evict 8 keys, but ours can evict 20. Consequently, we could save 37.5% more storage for expired keys and reach 100% utilization. Considering the computation overhead, both algorithms are old ones, while ours has an additional overhead on maintaining buckets. We may also double the storage memory for keys, but since we could evict more efficiently, our algorithm will have much fewer expired keys in memory. So in overall, our memory usage will decrease. In our algorithms, the number of buckets and base are two parameters, and we define the product of them the size of a bucket, which is the maximum time capacity for buckets. If base is fixed and we add more buckets, size will be increased. In this case, we can relieve bucket condition, but may have greater overhead on scanning buckets. If size is fixed and we add more buckets, base will be decreased. Then fewer keys will be in the bucket while more buckets will need to scan. The detailed analysis on parameters will be very interesting and we leave it to our experimental analysis. In our experiments, we use YCSB to send randomly generated requests and write a Python script to record the status of Redis for every second. We test on a server with 188 gigabytes memory and use the standalone versions of Redis 5.0 to implement our algorithm. For random data, each key is 8 bytes and each value is 1000 bytes. Our number of operations are from 3 million to 30 million. The workloads are combinations of probabilities of read, update, insert, and read modified write operations. TTL is drawn uniformly from 3 sets, only 60 seconds, 30 and 60 seconds, or 15, 30, 45, and 60 seconds. Moreover, we set the number of client threads from 1 to 4, because 4 client threads is large enough to reach the limit for the standalone version Redis. For buckets, since the maximum TTL is always 60 seconds, we have 3 sizes, 60, 120, and 240 seconds. For each size, we test base 100 and 1000, where each bucket stores keys in 100 milliseconds or 1 second. So in overall, we have 1 reference instance and 6 test instances. We evaluate our performance comparing with the baseline original Redis ones. As we can see, in overall, our algorithm can reduce at most 54% peak and mean memory, while it might increase 3.74% peak memory in worst case. The range of throughput improvement is between negative 11% to 23%. We would divide the short-term and long-term performance separately. For short-term performance, only 3 million operations are conducted. And as we can see from the left figure, the memory increases steadily and all operations finish at around 50 seconds. Before 60 seconds, which is 1 TTL. So no case can be evicted at this moment yet, and it shows the memory overhead for buckets. Actually, it is the only case for memory usage which will be increased. Another thing we can see from this figure is that When eviction starts, our algorithm can steadily and efficiently evict expired keys. Concerning the throughput, our algorithm has pretty low overhead. While short-term performance shows the overhead of buckets, the long-term performance shows the average performance of our algorithm. From the figure on the left, we can see when bucket size is insufficient, shown as the brown curve. The memory performance soon degrades to the reference case. For other cases, they could save almost half memory compared with the baseline. The throughput shown on the right indicates the effect on throughput is within an acceptable range. In the following discussion, we will only consider the long-term performance. As for the effect of size, our result shows that with insufficient size, say 60 seconds in our experiment, the performance would degrade significantly to the baseline, while it still suffers from the bucket's overhead. On the other hand, given sufficient buckets, our algorithm can significantly reduce memory within an acceptable range of throughputs. Considering the trade-off between the number of buckets and base, we can see in this figure the first and third columns are with base 100, while the second and fourth column are with base 1000. By comparing column 1 and 2, 3 and 4 separately, we can see that with larger base and fewer buckets, we will have lower memory usage, but the throughputs are also reduced. Our final observation is about our performance under multiple TTLs, since sometimes one database may need to have different TTLs for different applications. As the number of TTL increases, the randomness of expiration increases, and we are more likely to have bucket collision. As a result, our throughputs will decrease. However, concerning the mean memory, it has fairly low impact on cases with sufficient buckets, and it could relieve and improve the case with insufficient buckets. In conclusion, the eviction efficiency of expired data is crucial for a memory database, and the current Redis randomized expiration algorithm has some space for improvement. Our bucket-based expiration algorithm could significantly improve the eviction efficiency by using buckets to group keys expired simultaneously. The results show it can save greater amounts of memory and have an acceptable overhead on throughputs. To maximize the performance of our algorithm, a key point is to create enough buckets based on the maximum TTL. And that's all for our presentation. Thank you.